I tried to type up the list. Obviously, there might be some typing mistakes. That's one thing. But another thing is, okay, only one email bounced back to me, so there's only one email address that I got wrong somehow from your handwriting 2 days ago. Anyone who was not here on Tuesday, therefore you are not on this list. So you have to write your names in here. If you were with me last semester, then I don't particularly need your email address. If you have changed your email address, then please write it in here. I have changed my email address, by the way. So I have set up a new email account specifically for the Technical University only, for all my zillions of students. So, two things. Those who are new, please write your name, surname and name and email address and sign for today. But there's another thing. I want you to check this for typing mistakes. If there are any, correct them, but so that I can understand what the correction is. And there's another thing. I already mentioned it on Tuesday. Sometimes it's extremely difficult for me to tell which of the four is the first name, which is the surname, which is the middle name, which is whatever else. So I am trying to order everybody by surnames. So please, if you see that something is wrong, put some arrows, and I'll make a new paper for probably for, I'm not sure if maybe for next time. Who knows? So there's only one email address for now that needs verifying, checking, and correcting, but I have no idea. I tried to understand your handwriting as well as I could, and sometimes I really had no idea which is your first name, which is your given name, which is your surname. Okay. I bet you wouldn't understand some of ours. Especially those people who have written 4 names in a row. How on earth am I to know which is surname and which is your personal name? So please sort that out. Sort that out so that the next list is already decent. Also, please make sure if you have not attended Math 1 and if you have not done anything for Math 1, you have to go to Math 1. You can't be here because it makes no sense. I just had one student who somehow was unfamiliar to me and took Math 2 last semester. He retook the exam and barely could squeeze that 4, but he is missing Math 1, so now he's going to have to attend Math 1. So that this doesn't happen, please, those who belong in Math 1, go talk to Miss Agnes and do Math 1. Except, of course, those few people who have some parts left. 1, 2 parts of Math 1, that can be settled. But there, yes, that's okay. But I have at least one person who has done 0.
I know that person.
You know that person?
Yes, I met him yesterday.
Who's done 0 and therefore is being sent to Math 1. That's probably Miss Agnes assigned him to Math 2 by mistake. So now I assume there were 53 people on Tuesday here. Now, well, okay, on that paper there's enough space for 75, so I hope not more than 20 are coming today. Not more than 20 new people are coming today. All right. To everybody, once again, please make sure you do attend the lectures because later it will be much more difficult to catch up. If you miss something, Unless, of course, you know this material really, really well. That's not a problem then, but still, you have to be present for tests. All right. I found some leftover copies from previous semesters of last lectures material, so I didn't have to copy more papers, extra papers. So those people who were not here on Tuesday, who have not, obviously, because of that, haven't received my email with the material in digital format, then at the end of the lecture, or now, if you like, can take this. And I will pass the new material along soon. So this is the old material from Tuesday. Not anti-differentials, but the differential of a function. Today, we are talking about antiderivatives and integral notation. In other words, we are introducing integration, which, by the way, you did on Tuesday. That last exercise on Tuesday was all about integration. The operation opposite or reverse to differentiation. And today we are simply going to settle things, define things, and start seriously practicing. All right. So the process of finding the derivative of the function from finding the function from its derivative, or perhaps the function from its differential, is called antidifferentiation. Later we start calling it integration. For now we simply call it antidifferentiation because it's going backwards from the derivative back, from the differential back to the original function. That's why we call it antidifferentiation for now. And so the function, okay, let's take the black pen. So the function f of x is called the antiderivative or the primitive function, or the primitive function of the function f small x. So f capital and f small of x. So the f capital function is called the antiderivative or primitive function if, obviously, the derivative of this function. Now I'm not allowed to make any mistakes because it's almost impossible to erase them on this board. If the derivative of that function is f of x, the small function. In other words, if I derive this function, I get the primitive. I get the derivative. If I do the antidifferentiation, I get the primitive of that function, which is usually named f capital. So this process, antidifferentiation, finding the antiderivative or finding the primitive function. Of course, the term primitive is deceptive. There's nothing primitive about this. But primitive as in primary. Primitive as in primary. Primitive as the function that was there in the beginning before we derived it. The second definition, we already saw some things. Some people showed me some problems with finding the antiderivatives or antidifferentials last time of the trigonometric functions, that we had several versions of an answer. We should remember that the derivative of several functions could be the same. So one function could have several primitive functions. For instance, x squared plus 3x plus 7. The derivative of this is 2x plus 3. X squared plus 3x minus 100. the derivative of this is the same, 2x plus 3. So the antiderivative of 2x plus 3 could be this, or it could be this, or it could be x squared plus 3x plus any constant, because the derivative of constant is 0. And so we can solve all the functions in sets. So each set of functions will be the set of antiderivatives of some certain function. And therefore we have to introduce this integral notation. So we write the integral sign, which resembles the letter S. Yes, it does come from the letter S. Yes, sum. F of x dx. We write this dx thing in the end. The differential of x is f of x, one of those primitive functions, whichever you can find, this one, or without any constant term, plus c. C is a constant of integration, which simply denotes that when we find this antiderivative, this primitive function f of x, we may add any constant we like, and we still get a primitive function. Simply in one line, in one short expression, we write all the infinitely many primitive functions of this one. Infinitely many primitive functions for the constant equal to 0, for the constant equal to 1, for the constant equal to minus 100, for the constant equal to 2.73, and so on and so on. So this is the set of all antiderivatives of f of x, and this is called the indefinite integral. Indefinite because it could really be any value of constant. So it's not a definite function, not a strict function, but simply a notation that describes all the possible primitive functions. So this is the indefinite integral. It's a set. It's a set of all functions of this kind. So f of x, of course, is one of the primitive functions, but we could add any constant to that one. So what's the next thing? The next thing is, okay, some definitions. So the function f of x is called the integrand. Integrand, the function to be integrated. The function for which we are finding the primitive function is called the integrand. And c is the integrating constant, or the constant of integration. Sometimes, in some situations, we can even find the specific value of that constant if we know at least one point of the graph of that primitive function. So now, some laws of integration. So, first of all, the derivative of this integral, the derivative of this indefinite integral, the derivative of any function like this is, of course, the function f of x small. So, the derivative of this, if we derive this integral, we get the function f of x back. And on the other hand, we can write it as a differential. So I could write d of this. I could write d of this. So differential of integral f of x dx would obviously be the derivative times dx, as we saw last time. So differential of some function is its derivative, this one, times dx. If you remember, dy is actually y derivative dx. So if I write, if this is the y, if I derive this and the derivative of this is this, then obviously the differential of this is the derivative times dx. The differential of the independent variable. So that's the first law. The second law is what happens if I have to do it in the reversed order. Derive first, integrate afterwards. So we can reverse the order and we could try integrating the derivative of the primitive function. And if we do that, then see this, the derivative times dx is actually differential of that function. So it's d of f of x. And it must be, well, obviously, it must be the function f itself, because this is f small of x. So it must be the function f of x itself, plus c. So now what we see here actually is that integration, if we write it like this, integration is actually the reverse operation to differentiation, to finding the differential, not exactly to finding the derivative. Of course, technically, what we need to do, we need to find the derivative. But formally, we can see that it's actually opposite to the finding of the differential, because the integral sign and the differential notation sort of cancel each other out. So it's not exactly the reverse of derivatives of differentiation, but it's the reverse of finding the differential. So finer details, these. Okay. Some more laws. Okay. What happens when we need to derive a function multiplied by some constant? Derive. Last semester. So if I have to derive constant k times f of x, what did we do last semester in situations like this? We can take k outside and simply derive the function f of x. So if I can do this in differentiation, I can do it backwards as well. It works for integration too. So if I have to integrate the function k times f of x, f small, thinking ahead, f of x dx, then it actually is k times f primitive of x plus c. In other words, I can take the constant factor outside the integral. So there's no problem. It's the same as if I took this constant k and wrote it outside. Just push it out, especially if it makes a mess of integration, if it makes it difficult to see the function itself, then it's much easier to take it outside of the integral. In other words, if you multiply the function by a constant, you multiply the primitive function by the same constant, just like we did when differentiating, when finding the derivatives. Okay. What other rules or laws were there when we were finding different derivatives? Something simple. If I had to derive a sum of two functions or difference of two functions, yes, it was the sum of the derivatives, and in this case, if I have to integrate a sum or difference of two functions, then obviously I can write it as two integrals separately. Integral of f of x dx plus or minus integral of g of x dx. Please don't forget to attach that dx in the end of the integral. That's a very common mistake. People think it's not important and just skip it. Unfortunately, it is important. In some situations, it's impossible to solve the integral if you don't write it. It's impossible to solve differential equations if you don't write it. So it's not just like that. We want you to write it. They are necessary. And better get used to writing those. What else is there? Now one very specific law. If we have an integral and we know its primitive primitive function, if we know an integral and we know its primitive function, then the rule is it works even if we replace the variable x by some specific function or expression. In other words, if we get a composite function, for instance, it's not f, not just f of x, but f of some expression u of x perhaps, by the differential of the same function u, then of course it's the primitive function of u plus c. In other words, we can replace expressions, we can use substitutions. In this case, of course, u is u of x, some function in terms of x. So if I know, we'll just have a look at some examples, some very simple examples. For instance, do we know what the primitive function of, let me think of something clever, extremely clever. For instance, 5x to the 4th dx is?
5 over 5. 5 over 5.
X to the fifth. Remember that when differentiating a power, we take the exponent, make it the constant factor in front, and the exponent is reduced by 1. So x to the fifth plus c. And now imagine that I have an integral 5, let's say, sine x to the 4th, and d of sine x is there. D of sine x, by the way, what's that from last time? Cosine x times dx. In other words, if I have something like this, 5 cosine x sine x to the 4th dx, it's this, because d sine x is cosine times dx, right? So it's the same thing. If we see something like this, we think, okay, cosine is the derivative of sine, therefore we can take cosine and dx together, they make this, and now I have 5u to the 4th du. So now I think it's integral of 5u to the 4th du. And according to this fifth law, the form is the same. This is called the law of the invariance of form. Invariance means not changing. The form, the total form, the overall form is the same, even if the expressions become more complicated. But if you follow the pattern, if you see exactly the same here and here, then the overall expression, the overall form doesn't change. So the result of this would be sine x to the 5th plus, of course, a constant, or sine to the 5th x. I'm writing with brackets simply to preserve the form so that you can clearly see that the form is exactly the same. So here we can recognize the form is exactly the same as this. So if we know how to do this, we know how to do this, which, well, at the first glance, this looks like quite a complicated integral. We will not do something like this today. I think I'm simply introducing this law. We will elaborate on this next time. Today we are simply going to practice some integration. And now, okay, antiderivatives. Ooh, could you please raise your hands again? Who is new today? Okay, let's hope there's enough. Let's hope there's enough papers. Let's hope there's enough papers. Okay, you could just start passing things along. Let's see. Take one past the rest along. Let's see, I hope.
No.
Nobody understands this. Of course, makes no sense.
At least something. Okay, I need to make more copies. Sorry. So try to spread them out evenly and then I'll give a copy to everybody who's missing. Okay. Okay, there's one more. Which area has nothing at all? You have nothing at all. Alright. Try to cooperate for a while. So I will be back in a few minutes. I'll just make some more copies. So it simply means that the machine probably ran out of paper and they didn't notice. Okay. So you see a reminder for the basic integrals, which are, of course, the reversed formulas for differentiation. Now I wrote them in the reversed order so that you can integrate. Some basic formulas. Try to apply them here. I think the first few examples are extremely simple. If you see a sum or difference, you can integrate them separately. If you see a power, pay attention what happens when we integrate a power. Exactly the opposite. We increase the exponent by 1 instead of decreasing, and we divide instead of multiplying, and we divide by the new exponent instead of the old exponent. So pay attention to these formulas and try to start doing these exercises. The part that's called homework or extra practice, that's simply an old title. It's just extra practice because I'm not giving you homework as I have no time to correct it. I'll be back in a few minutes.
Yes, I understand. But I mean, it's not XA.
We take this. X in the power of 10 divided by.
There's no number in front. Let's just
That's why, because we divided because there is no number. Because if there's a number, then
Okay. Is the attendance sheet still traveling around?
No.
There, okay.
Can you help us with the third?
Number 3. Okay. Let's have a look. So I do hope that number 1 and number 2 are easy. Okay. Well, in fact, number 3 is easy too. So if you come to integrate 3 to the power x plus 2 dx, obviously, we see 3 to the power x is in the form a to the power x, for which we have an integral in this table of basic integrals, first column, last integral. So it's 3 to the power x divided by natural logarithm of 3. Now I have plus 2x, yes. Now I have a request. I know that some people like to write log without any base for natural logarithm. Some other people and some other textbooks like to write log without the base for decimal logarithms. Because there are conflicts and misunderstandings, don't write log without a base. So either you write ln for log to base e, or write lg for log to base 10, or write down the base that you mean. Because if you write simply log, I cannot guess whether it's this or that. And therefore, either write ln for natural logarithm and lg for decimal logarithm, or do write the base. Otherwise, it becomes extremely confusing. And so too, how do we integrate the constant 2? What is the derivative? Well, of what is the derivative equal to 2? 2x. So it's plus 2x plus, of course, a constant. If I derive 2x, I get 2. If I derive 100x, I get 100. So when I integrate a constant, the integral of a constant is obviously this constant times x. So that's again something that you perhaps might want to write as another basic integral. If you can't figure out it by yourselves, then kx k, which is a constant, k dx is kx plus c. If k is a constant, of course, it's not a function, it's not a variable, it's some constant. So if I have to integrate 2 dx, I get 2x. If I need to integrate pi, I get pi x. If I need to integrate 100, I get 100x. Number 4. Remember how to deal with rational exponents. How to change roots into powers.
Yeah.
So if I have x to the power 5 times cube root of x dx, it actually is x to the power 5 and 1/3. 5 and 1/3, because remember the nth root of x is actually x to the power 1 over n. Remember the laws of algebra for changing roots into exponents, roots into powers. And on the other hand, if I have x to a negative power, negative exponent, it means 1 over x to that power. So just very basic things from algebra which you should remember from, school. Okay, so now I can apply the first rule, x to the power a, integrated, becomes x to the power 1 greater, so it's now 6 1/3, divided by the new exponent, this one, the same, 6 and 1/3 plus c, and of course I can try to change this. This would be 19 over 3, so it's 3 over 19, and this would be x to the 6th times cube root of x plus c. If you do this part correctly, I will not force you to do this back again if there's no time, for instance, during a test. But this is not a nice way, this is not a nice thing to write in the denominator. You should be able to find a reciprocal fraction and write it correctly. Alright, 2 over x. 2 over x. If you pay attention to this, so 2 over x to any other power would be a power, and the integral would be a power. But if we have a number over simply x, that's the one exception where this law doesn't work. If the exponent is -1, so 1 over x the anti-differential or the primitive function of 1 over x is natural logarithm of x, pay attention, absolute value. Absolute value. Why is it absolute value? So now the integral of 2 over x plus 3 over square root of x dx. So this would be 2 ln of x absolute value. So either write ln or write log to base e. Don't write just log without anything. Why absolute value? In the integral itself, if I'm not looking at this part, in the integral itself, there's nothing for this to indicate that x couldn't be negative. X can be negative. This function itself has nothing to do with the logarithm. When we integrate, all of a sudden we get a logarithm. We know that logarithm is defined only for positive values of x. And therefore, it can also be proved that for negative values of x, we would still get ln of the positive value, the ln of the absolute value of x. It is possible to prove that it works for negative x values also, but you have to put the absolute value on x. In this case, though, because it's square root of x, the x is forced to be positive only in this case. But generally, if you have doubts, then it's better to always put this absolute value sign. And sometimes it's unnecessary because x has to be positive by default for some reason from those functions. Now, what? It's 3 times x to the power minus 1/2. Negative because it's below the line. 1/2 because it's square root. So now to integrate this, I have to add 1 to this. So it will be 3 to the power x to the power 1/2. The new denominator, I add 1 to this, get positive 1/2. Divide by the new exponent. So 2 ln of x plus, now it becomes 6 square roots of x plus 6. Now this is the answer. This is now the answer. So I guess that for the beginning, this kind of thing, integrating these powers, is probably the most difficult part because everything else is in the table of basic integrals. So that's where you need some practice. All right. I might email you the answers now, if you like.
You have to take each video. Yes.
Nothing.
We do.
You again? Oh, okay. Actually, no, not all of it. Almost. Go have coffee. Something. Let's see. This. Okay. Now, math 2. Yes, math 2. Answers. Okay. I am. Okay, I'll just email you the answers. Yes, okay, I will send it to you in just a moment. Let me send this off. Send this. Okay, now I will send you the next file.
No, I see. Forget this now.
Okay, check mail. Send it. So you have to write it very, very clearly. You cannot write it so that I can afterwards I can write it correctly. And last name first, surname first, first name last because I did it. Okay, well, you want to hear last name. So this is your last name, this is your first.
Plus C.
Okay, what did you do that in this
I didn't see your name on the paper. No. I'm talking about Tuesday. I'm talking about Tuesday. You want to do this because I put only people who are here on Tuesday. So these people who are here on Tuesday, they go. Tuesday. So okay, I'll put you on the list and